Hello guys, happy to be back here with you in the second part of AI in Space Tech, and here I'm going to be discussing the knowledge section. So in the knowledge section, every time I will be doing a video in this second part after the news, I would like to introduce scientific paper into simple terms so everybody out there can understand it. So I'm going to be taking a work from the academia and I'm going to be breaking it down in very simple terms for you so probably everybody can understand it. So that's my goal here, and of course you're free to comment, to ask me questions if you don't understand, give me your feedback. Please like this video or dislike it if you think it's not good, so I have a feeling how should I proceed with this work. So please be very open, talk to me, tell me what you think about the work. So of course don't forget to subscribe to the channel if you find the content interesting, and also click the bell button so every time you're notified when I'm doing a new video. So in this week I'm going to be talking about a work I did. The experiments were done in late 2015 and the work was presented in a conference, I guess with great success on summer 2016, and this is my work, but my goal here is not to present my work. This is the first time I'm doing this, so it's easier for me to present one of my papers, but I would like every week to present something else, and obviously not my work. But for this week I'm gonna show what I had already done because it's easier. So the paper I'm gonna be presenting, it's called Semantic Segmentation of Aerial Images with an Ensemble of CNNs, and practically what we did here was to use convolutional neural networks, or CNNs, this is the abbreviation, and this is practically the best model from the deep learning field for the processing of image data. So the big breakthroughs in image classification, in image segmentation, actually have been done with these CNNs, or convolutional neural networks. And here I'm using them for semantic segmentation in aerial images, and what I'm doing is that I'm creating an ensemble. An ensemble is practically multiple variations of the CNN model, which I'm using as different classifiers. I'm classifying independently with these variations of CNNs, and then combine the result to get some better outcome. So this is the paper, and I'm going to be adding a link to it. Everybody can download it, everybody can read it. It's in the internet already. You don't need to be registered to any library or to any institution to be able to download the paper. Is open access. So I'm not going to be presenting you, of course, the topic through the paper, but I have a presentation. So here we are, and let's start. So the topic is semantic segmentation of aerial images with an ensemble of CNNs, and this work was presented in ISPRS Congress in Prague in the summer of 2016. Here you can see me and my collaborators, and this work was mainly done in ETH Zurich, where I was visiting scientist this time, but of course with the support of everyone here. Some people are from ETH, some people are from DLR, and of course my professor in Technical University of Munich. So the presentation outline is as follows. So first we will introduce a little bit the CNNs, or convolutional neural networks. I'm going to be briefly talking about how they work. And then I'm going to be moving on with the proposed modified model and the architectural properties that contains, and then I'm going to finish with experimental result over a particular data set. So let's move on. So where do we start? Of course, we start by explaining the convolutional networks, or CNNs. My scope here is not to explain them in very many details, because I guess out there's hundreds of tutorial videos dealing exactly with that. But I would like to give a quick overview or refreshment to the people who don't really remember how they work, so you can get a feeling. So practically, we start with an image, or an image patch in our case, and in this simple example we have an image patch of 32 by 32 pixels, and what we do is that we convolve it, or convolution actually stands for filtering. So practically we're convolving or filtering with a small filter, and we get an output. This output from the filtering, it's called feature map. And we don't convolve just a single time, but many times. So we get many of these feature maps, as you can see here. Then we have a pooling operation, where pooling practically stands for a shrinking operation. So for example, a very popular pooling operation is a max operation in a non-overlapping window. So practically you move within the feature map and you just take the maximum value within a, let's say, 2 by 2 window. And then you end up with the same number of feature maps, but now they're shrinked in the spatial dimension. And then what you do is that you again convolve with a new set of filters, and as you convolve you end up with more feature maps, because you're practically using more convolutional filters. Of course, the output, it's again small, then again you're pooling, again you're convolving, you're again pooling, and in some cases after quite deep networks, we practically have a fully connected network, and this stands if we would have a single pixel, if we can say pixel, practically a single feature element deep inside the convolutional network. This now connects with every other feature in the next layer, so we have a fully connected neural network deep inside the structure, and then comes the classifier in the very end. And this kind of altogether, this structure, generally it's called convolutional networks. So what are the characteristics? Some general characteristics of these is that in CNNs, or convolutional networks, we have an automated generation of features. So we don't need to do anything. We provide the raw image and we let the system create all the features that will be used for the classification. So practically this means that we don't have feature engineering. So in satellite image, for example, you wouldn't need to think about NDVI, I don't know, filtering, pre-processing the data, but you would rather give the raw input. So state-of-the-art results, that's another property. So with CNNs, we've seen that it's proven nowadays that you can have the best output in tasks such as classification, semantic annotation, and this is in computer vision and in remote sensing. And the first thing is that they're very efficient for large image extents. And this is a little bit more technical, but practically what we're learning here, what you're trying to learn in a convolutional network, it's a set of good filters. So practically you're trying to learn these features, these filters that produce the good feature maps. And we missed this one. Practically the property here is the weights, as we name them, or practically the values of the filter are shared. And this means that a small set of values within the filter are being used to convolve the whole image. So a small set of filters convolve the whole spatial extent of the image, or the feature maps in deeper layers. And these are very, very important characteristics of the CNN. So when we talk about semantic segmentation, practically in remote sensing, we generally use the term classification. But classification term is wrong, because in computer vision, classification means something else. So I'll be using the term semantic segmentation, and people who used to call this classification, they should revise and use the term semantic segmentation instead. And what we do in semantic segmentation is that we start with an image, we process it, and on a per pixel basis we provide an output class that we have defined from the beginning. So the CNN method has some strong points. It doesn't have ad hoc rules, so there's no general assumptions. It's an end-to-end training system, so this means from the moment we start using the CNN, we have generally minimal interaction with the system. We allow the classifier to build the features and classify them itself. And this is very, very beneficial. Of course, there's minimal pre and post processing, or we can even completely skip these steps, so we can avoid completely the pre-processing and post-processing. Generally, these kind of systems, they're very slow during training, but during inference, prediction, when we say inference, we mean prediction, they're very, very efficient, they're very fast. And of course, even though it may take some time to learn a set of good weights, to learn the good kernels for the convolution, practically this is not one-time thing, because we can reuse the weights. This is a very, very important property of the CNNs. We can reuse the weights for another task and have better results just starting with random values, because one can initiate the filters I showed before with random values. But what we've seen is generally in practice is that it's much better if we start with a good set of weights from a previous problem, even if it's different one. So the weights we learn, the filters we learn for the convolution can be reused. And of course, what is important also to underline is that this kind of system produce the best results we have until now on tasks such as semantic segmentation. So moving on. So the proposed model has some architecture properties and some major components, and these are first of all, we have to convert the network from a standard neural network to an FCN. And FCN, if you read the paper, stands for fully convolutional network. So I'm going to be discussing all these properties in detail, but now I'm just mention them quickly. Then we have the property of upsampling that we have to look into. Generally, the network is not sequential, but it's a direct cyclic graph architecture. We have deep supervision in our system, and I'm gonna, as I said, introducing all these concepts in detail. It has dual processing stream for multimodal data processing, and then in the end we also have a convolutional neural network ensemble that I'm gonna be discussing. So let's start with these components. So generally a network, as I said before, it starts with an image, then comes the network, and very deep in the structure we have fully connected networks, and then we have the classification. And the classification, which this is the correct term of classification, is practically that we're getting a set of classes, and the probability of containing these class in an image. So in this case we have an image with a car, and the system may see the probability of each of the independent classes, which are predefined, and say, okay, here is the maximum probability, and this probability it's assigned to the probability of the car. So probably the image contains the car. But in our case, we're not interested in the classification task, but in the task of semantic segmentation. So to do that, we just have to convert the neural network in a fully convolutional one. What this means is that we practically repurpose these very deep layers into the same structure in a way that we don't these used to be here fully connected, so each component was connected to the next component in a fully connected manner. And what we did here in this paper is that we repurposed these to be convolutional layers. So we repurposed the fully connected into a fully convolutional, and that's why we call it FCN. And what this does is that instead of giving us these probabilities that we had before, to give us a full annotated outcome per pixel. So this is the first major component. Further on, what we need to think about is upsampling. So upsampling practically learns to resize a deep representation into the input resolution, and this compensates for the lost spatial resolution due to the pooling as we shrink, but it doesn't compensate for the very fine-grained details which were lost. So a visual example is that we have the image, and as we have the pooling layers, we're shrinking and shrinking and shrinking, and then we have a very small representation, and with the upsampling we can actually build back the full resolution that we had before, but we cannot compensate completely for the lost fine-grained details. So we can upsample, but it's very hard to retain the sharp edges that we had before. So for overcoming the problem of the lost fine-grained details, what we do is that we create a direct acyclic graph. And this means, in very simple terms, is that we don't have a sequential architecture with an input and an output. So this is a sequential architecture. Here we start with the input, we have the convolutions, the pooling, convolutions, pooling, and so on and so forth. But what we do is that we create additional connections. So we have here the output, where we have to upsample it 32 times to get back into the input resolution. And what we do is that we upsample it by a factor of 2, so now it's 16 times downsample. And what we do is that we introduce a connection from this layer to this upsampled information, and this compensates slightly for the lost fine-grained details. And to improve more, we introduce more of these connections as much as our hardware allow us, and in this way and in this paper we actually ended up having a representation eventually that needed to be upsampled 4 times to meet the input resolution, where if we would just have used the sequential architecture, we would have a representation that would be needed to be upsampled 32 times. So this restored somewhat the lost fine-grained details. So another component that we introduced is the Deep Supervision, and Deep Supervision stands for the following thing. So in a standard neural network, we have the convolutional neural layers, and very deep in the structure we have the objective function. So objective function is a mathematical function that practically measures how well we did in the prediction during the training time. And so this function here tells us how well or bad we did, and based on this we update all the weights sequentially on every level so that we improve on every iteration. So what we did in Deep Supervision is to copy this objective function. So practically we copy the same objective function and introduce it into earlier layers. In this way, practically what we do is that we have the following improvements. So we managed to improve in our particular data set by more than 1% by introducing these 3 objective functions. We speeded up the training, and this is partially due to the resolve of the vanishing gradient problem. I'm not going to be talking very much about the vanishing gradient problem because I have to get into the optimization aspects of the network, and I guess these are very mathematical details that I don't know how much are interesting for the average viewer. But if you're interested, you can definitely find many videos in the web, or even tutorials and books talking about the vanishing gradient problem. So anyway, what we did is practically we speeded up the training, because these systems are slow in training, and these additional objective functions allow us to be better in the training time. And of course it acts as a regularizer, meaning that we get better representations, better feature maps on every level here, instead of just having one objective function in the end. So the complete architecture, you can see it here. Maybe the graphics are too small, but what is important to see is that there is a gap here in between, and here we have the input image, and here we have the input DEM. So we have an image, and the DEM stands practically for a 3D model. So we have the same copy of the network processing here the image component, and here processing the 3D model. And very deep in the structure, we have a concatenation of the features and further further processing until we get here in the end. And here in the side, practically you can see the direct acyclic graph. So as we said, we don't have a sequential network, but we practically have connections that skip big parts of the network and connect earlier layers with deeper ones. And this is what you can see here. So with this architecture, we have the following characteristics. We have 20 plus nonlinear processing layers, and for today's standard, that's a rather small number of nonlinear processing layers, but back then in 2016, practically, this was quite a large network based on the standards of these days, because of course with deep learning you have very quick advances. So what was the state of the art 2 years ago, it's already very old in some sense. But nevertheless, this was a great achievement back then. This is a non-sequential architecture. I talked a lot about this direct acyclic graph. And as I said, we have two parallel processing streams with two input modalities. So two different sets of data, DEM and image. And the pros of this architecture is that we have an end-to-end training. As I said before, we have the transfer learning. So what we're going to learn here, we can reuse it in the next application, probably in remote sensing. And we have a large prediction path size, namely 259 by 259 pixels. So we provide an input of 259 by 259 pixels, and this is what we get in the output, which is quite large. And the cons of this system is that it's rather sensitive to hyperparameters. Of course, to train these networks, you have some few parameters that you have to tweak, and the system is rather sensitive in the choice of these few parameters. And then of course there is a high computational cost, which is not so high, I guess, for nowadays standard. We use the top-notch graphic card, but these are not very expensive. So the graphic card practically we used cost about €1,000 today. But I don't think this is very expensive considering the networks you can run on this graphic card. So the graphic card is an NVIDIA Titan X with 12 gigabyte of DDR5 memory. So, of course, as I said before, the network was trained as an ensemble, and in CNNs, or generally in deep learning, what we know is that to use a good set of weights or convolutional kernels in our case, it's good and improves the accuracy. So instead of starting with random values in our weights, we start with a set of pre-trained models or pre-trained weights. And what we used here was the Pascal VOC from Long et al. That's a semantic segmentation task. We use the weights from the ImageNet classification. So this is not semantic segmentation, but a classification task. And ImageNet actually is one of the biggest, if not the biggest, I'm not sure anymore, The ImageNet is the biggest image classification database in the world, so we use these pre-trained weights, and we used also the weights of the model of the places dataset. So the places dataset, it's indoor and outdoor image scenes, and it contains some millions of training instances. So all these weights were exactly the more or less the same architecture, and what we did was just to load them into the same network and train the different Ensemble instances independently. But practically you have one network and you just initialize it 3 times and you train it. So some information on the training and the inference. So we constructed this whole framework back then with the CAFE framework. Nowadays the CAFE it's not actively supported anymore, so it's dying, but there's CAFE 2, which probably it's very similar to CAFE. CAFE 2 is supported by Facebook. I haven't worked with it, but I guess there is very good documentation, and probably of course I'm not sure about these things, you can modify a CAFE model into CAFE 2 model. I guess that would be possible considering the fact that the CAFE 2 is based on the CAFE library. Anyhow, so back then we used the CAFE. The model optimization was done with stochastic gradient descent with minimaxes, momentum, and L2 regularization. And these are just some more or less nowadays standard details for the training of these big networks. And it's almost by default that you have these properties. And of course, as I said before, the training takes quite long. So for having optimal results, we trained the network for about 2 days on an NVIDIA Titan X GPU, as I said before, these GPUs, which cost about €1,000. And the inference, so the prediction per tile of 259 by 259 pixels takes around 0.2 seconds using a single model, so not the ensemble, whereas the inference on the complete aerial image that we used takes about 2,500, of the image, which is about 2,500 by 3,000 pixels, takes about 9 minutes on the ensemble, but this is because we have very large overlaps. So for having better results, of course, we are overlapping the predictions as we move along the image. So that's why it takes 9 minutes. If you want smaller overlaps, I'm sure you can decrease these in a few seconds if you really don't even want to do overlaps. So some quantitative evaluation. Practically here we used the ISPRS benchmark dataset. This is an open benchmark dataset. Particularly we used the ISPRS Vaihingen dataset, and these are our results. And these are on the validation test, on the validation set. And what you can see here is the outcome when we use all 3 models, so all 3 ensembles. And yeah. And here is when we use 2 models, and here is when we use each independent model on its own. So if you look carefully the numbers, or you can find more details in the paper, practically what we see is that we perform better when we use 2 out of 3 ensemble models. Of course, the difference when we use all 3 ensemble models is very small. So with 3 models we perform 85.7%, whereas with 2 ensemble models we have 85.8%, and these 86 here if we add the post-processing step of fully conditional random fields. And this is just a post-processing step to push further the accuracy, but practically the outcome was 85.8. And Here you can see the independent models, and as you can see, the places pre-trained model doesn't perform so well as the others. So this is also obviously in the statistics. So here are the results on the test set. So the validation set, we created this ourselves, but the test set is disclosed, and you have to submit your results to the committee, and then they validate it for you. And what we can see is that we perform even better than our validation set with an overall accuracy of 88.5. And with this 88.5, by this time of the submission, we were ranking on the second position, 0.6 behind the best scoring model, which was done by another colleague. But our process was fully automated, where their process had some additional hand engineer features and so on. Okay, this is the interesting part, I guess, for you. It's the qualitative evaluation, and you can see an input image here and what actually the model was predicting. And what is interesting to see is the difficulties and the level of detail. So for example, here you have a balcony, and in between you have two houses, and practically, sorry, the balcony stands in between the houses. So what is this balcony? Is this impervious surface, ground, or should we consider it as a building class, the blue class? It's really hard to say. But personally, I don't know. I would have to ask the people who decided how to build this benchmark. So yeah, the system here assign it to the ground class because this is more logical, but nevertheless somebody may say, okay, this is part of the building, so it's a building. What is interesting to see, however, is that on this balcony we have a few trees and some bushes, and you can see here that the system actually detects the bush, detects this larger bush here, and assign it partially to the bush class and low vegetation, and then partially to the tree class with the green color. So, well, yeah, quite interesting. We see it even detects the tractor, even though it haven't learned to, it was never trained on tractors. You can see with yellow here, we're actually detecting the tractors. And we even detect this this vehicle that it's behind this small tree. Partially here we can see small parts of it have been detected. So I guess quite interesting results, but what is important to notice is that the buildings are over smoothed, so we don't have these very sharp edges that we would like to see in the building class. We don't have straight lines. We have some wavy patterns, and sometimes in the corners you see we have an over smooth effect, and this is a little bit problematic, especially for visual purposes. And another example, if we look on a larger area, some difficult pattern here of buildings with very straight edges, and as you can see, these straight edges, what I was talking before, it's very, very visible here. So again, quite good result, but these straight edges that we would like to have are missing. So of course, in the Vaihingen benchmark, I've noticed a lot of small mistakes, and other researchers have noticed the same. And I guess this plays a very important role because the results nowadays are saturated. The accuracy is very, very high. Nowadays, even overpassing 90%. And of course, if you have a lot of errors, practically this means that now the best thing to do is practically to fit the errors of the annotators and not anymore try to be precise. And if you look in this very small image that I randomly found, and people have many of these examples, you can find some of them in my paper. you can see here that, for example, this part here of the building, which is actually not a building, we have a building here, house, and here we have a garage, and here we have a garden in front of the house, and this is annotated here as building. So this is wrong. This should be low vegetation, should be impervious surface, should be these kind of classes, and not, of course, building. Here, if you look down in the labels, I made a mistake. So low vegetation should actually come with the car color, and the car color should come with a low vegetation. So these two labels are vice versa regarding the color, but you can really see here the problem. And of course, this is not the only problem. You have these balconies here that are completely excluded, or these small impervious surfaces that are annotated as low vegetation. So these kind of small mistakes have to be corrected when you have accuracies over 90% that we are now stating on this benchmark. So conclusions and feature work. We built here a fully end-to-end training model with top performance, and of course this has practical impact, because in remote sensing, in the literature, scientists say that something that has accuracy above 80% can be used in practice, and here we have almost 90% accuracy. So future work, what would be very interesting is to have a class transition in the final annotation by learning the class contour. So by that I mean we could learn practically edges that they're class related. So instead of learning a pixel by pixel annotation, we can just learn the contour of the particular class and encode the class transition information between two classes within the edge. And this would probably allow us to have sharper transitions between the classes, to have better outlines rather than focusing on the inside part of each object. And another very interesting thing is to investigate different architectures for this problem. And in follow-up work, I actually worked with different architectures on this problem, and I improved even further the statistics of the particular benchmark. So with this, we're coming to the end of this session. I hope you learned something. If you have questions, don't hesitate to write them down in the comment section. I would really like to get back to you, reply to your questions and so on. If you would be interested in the code, sorry, I guess I haven't uploaded the code, but nowadays it's quite I guess it's quite old. In my follow-up paper, I had made better models, and I have uploaded all the code online. You can download it, you can use it, you can play with it, you can improve the models and resubmit them. So I think it doesn't make sense to upload these older codes. Are the ones I already have online are better than this particular model. So what else? Please give me your feedback. What would you be interested in looking into the next knowledge section? What you would like to break down and discuss about? And with these, I think I'm coming to the end of the session. Give me your feedback. Like this video or dislike it if you're not interested in the content, and let me know what's your opinion about this work. I hope you learned something. I hope you are a little bit smarter, or you got some new ideas on what would you be interested in implementing. And with these, I'm gonna say goodbye to you. So see you next time. Bye bye.